Good morning. So I am E. Ilavenil and we are going to see centroid of areas today. So centroid. So we often assume the distributed forces acting on a body to be a single force acting at a single representative point, because most of the forces are never concentrated on a very single infinitesimally small point. It is distributed over a small area or a particular line, which we often need it to be assumed concentrated on a point. So that single point is called as centroid. So centroid in 2D is marked by the point x bar and y bar. So when we consider the weight of a body, so W into x bar is equal to integral of x dw, and W into y bar is equal to integral of y dw, which can be conceived from the very basic principle. So here capital W is the overall weight and dw is the elemental weight. With this basic concept, so if we divide this integral x dw by capital W and integral y dw by capital dw, we get x bar and y bar for a mass or a volume. So here we are going for the study of centroid of an area. So a thin lamina is often referred to as an area. So for a thin lamina, the density rho, thickness T and area A, then its weight is given by capital W is equal to rho G A T, where often rho G and T are constants. Normally the lamina are of constant thickness, and rho, the density, is same for a particular material, and G is the acceleration due to gravity, which is a constant at a given place. So now if we remove these constants in our previous equation that we have seen, instead of capital W x bar, here we get the equations as A x bar is equal to integral x dA and A y bar is equal to integral y dA, giving us x bar and y bar by dividing integral x dA by A and integral y dA by A. Composite areas. When two or more areas join together to form the whole area, we call it as a composite area. So area A is equal to A1 plus A2 plus and so on. Actually, it may be our perception, and we conveniently call some areas as composite area because we divide it as per our need. A trapezium, we may say it is a single area, particularly in terms of our study. When we go for calculations, when we know the centroid of trapezium with a single formula, we can take trapezium as a single area, whereas if we don't know the formula for centroid of a trapezium, we can divide the trapezium into two triangles and a rectangle, as well as we can simply divide it into two triangles. Either way we divide it, if we know the formula for centroid of triangle and rectangle, we go for finding the formula for centroid of a trapezium through composite areas formula or the method of finding centroid of composite areas. So for composite areas, instead of the integral sign, we go for summation here, as there are definite number of independent areas which are available by dividing that whole area. So here ax bar is equal to sigma xa and ay bar is equal to sigma ya, or x bar is equal to sigma xa by sigma a and y bar is equal to sigma ya by sigma a. Here x bar is equal to a1x1 plus a2x2 plus and so on divided by a1 plus a2 and so on, which are the sigma terms. Similarly, y bar is equal to a1y1 plus a2y2 plus so on divided by a1 plus a2 plus and so on. So for standard shaped individual areas, we go for the formulae which are obtained by integration. So already we have seen the formula for centroid by integration. So we have seen it here. X bar is equal to integral x dA by integral dA, or simply a. So with this type of formula, we get standard shaped areas, the centroid. But now we have those centroidal values already found out by integration, and those formulae we use them in the composite areas for finding x1, x2 and so on. So here we have centroid of area formula for certain standard shapes. So we have a rectangle where the x bar and y bar are given by b by 2 and h by 2, whereas the area is given by bh, which is very well known. So for a triangle of this nature, we have x bar is equal to b by 3 and y bar is equal to h by 3 with area bh by 2 or half bh as we say. For a semicircle, x bar is 0 where it is considered from this y-axis. So it is at the center, whereas this height at which y bar is located is 4r by 3 pi, and the area we know it is pi r square by 2. For a quarter circle, both x bar and y bar are given by 4r by 3 pi and the area is pi r square by 4. So here we have a parabolic segment. So in this parabolic segment, the x bar is given by 5b by 8 and y bar is given by 2h by 5. So the area of the parabola is given by 2bh by 3. So here we have the complement section of parabola. So here x bar is given by 3b by 4 and y bar is given by 3h by 10, and here the area is bh by 3. So here we have a sample problem where we find the centroid for a composite area. So here there is a composite lamina which is available here with one triangle here one rectangular portion here, one semicircular portion here, and one circular portion which is being cut off, which can be considered as a negative section which has to be subtracted. So we have for the area addition of a rectangle, triangle, semicircle and subtraction of a circle. So here we can find out the centroid with taking any x and y axis as reference, but here we take this as y axis and this as x axis, because of which the triangle available here comes under the x axis, or say it is in negative y. So here, according to our formula, we find the area of the rectangle, area of the triangle, area of the semicircle and area of the circle, and for sigma A we add the first three and subtract the fourth one to get the sigma A of this entire area. Also we have to find x1, x2, x3 and x4, and y1, y2, y3 and y4, which we have obtained separately with respect to these axes. So we have x1 here, x2 here, that is taking this as 1, 2, 3 and 4. So this x is at the center of, x1 is at the center of this rectangle, and x2 is at the 1/3 of this triangle, and this x is at the center of the circle and the semicircle, whereas this is again at the center of the circle. So corresponding distances are taken and marked here. Similarly, y bar taken at the same places, but when it comes to this triangle, this y2 is marked negative. So we have a set of x1, x2, x3, x4, y1, y2, y3 and y4. So here we get sigma xa by having xa1, xa2, xa3 and xa4. So all the x1 into a1, x2 into a2, x3 into a3 and x4 into a4 are multiplied and obtained here as sigma xa. Similarly, we obtain here x1 y1 plus x2 y2, y1 a1 plus y2 a2 plus y3 a3 plus y4 a4 to give sigma ya. So we have sigma xa and sigma ya here to finally get our required centroid. So this is how we go for finding the centroids. Thus we can find centroid of any area which can be divided into a number of known shapes using basic formula and the expression for composite sections. Non-standard unknown sections shall be studied for the centroid by studying their geometry and going for integration, and even by some approximate methods. Thank you.